Hi everyone, I'm Niloofar Toorchi, member of technical staff at Open Networking Foundation. In this demonstration, we are going to show how WCMP is enabled in SONiC using pins and ONOS. First, I'll walk you through some slides explaining the need for WCMP and the changes needed to be made on pins and ONOS in order to implement it. Then I will hand it over to Daniele to show you the WCMP behavior in a live environment. Software-defined network, as you may know, enables many features and capabilities that are difficult to achieve using traditional embedded control planes. PINs as P4 integrated network stack adds SDN capabilities to SONiC, which is a widely deployed network operating system. There are many SDN use cases that are not supported in PINs. The focus of this demo is on weighted cost multipath or WCMP. Now let's talk about how WCMP can improve the network functionality. WCMP distributes traffic flows on multiple links proportionally to the assigned weights, and this helps optimally distribute traffic in unbalanced networks, which is the case in real data centers. There can be multiple reasons networks are unbalanced, such as using heterogeneous devices from different generations, link failures, and so on. If you are interested to know more about WCMP and how it outperforms traditional solutions, watch the Google's presentation in P4 workshop previous year. Here is the link to the presentation at the bottom of the slide. In this work, we implement WCMP using the open source ONOS and SD-Fabric platforms. SD-Fabric is a P4 programmable network fabric that includes ONOS as the SDN controller, running several applications, including SD-Fabric control application, and a leaf-spine fabric of programmable switches that in our case they are running pins. SD-Fabric control app computes the flow objectives, which are translated into flow rules thanks to the pins driver. Flow rules are stored into the ONOS core, which is distributed and highly available. Flow rules are then adapted to P4RT table entries and action set that are pushed to the devices. SONiC is adapted to work with remote SDN controllers by adding the support for P4 runtime protocol. SOI pipeline in SONiC is modeled in P4 and is referred to as SOI.P4. The P4 runtime service on pins translates between P4 entities and the corresponding SOI API's call. A response pass is used to immediately inform the controller when an update succeeds or fails, compared to the fire and forget approach of the other SONiC apps. Remote packet I/O capability is also added for the SDN controller for link discovery. SD-Fabric supports the traditional fabric features such as bridging at the leaf, equal cost multipass routing across the fabric or ECMP, which is a simple case of WCMP when all weights are equal to 1. IPv4, IPv6 unicast multicast, dual homing, DHCP relay, and access control list to drop or redirect traffic. Besides the traditional features, SD-Fabric supports some advanced features such as P4 forwarding pipeline, which is referred to Fabric TNA.P4, inbound network telemetry, and network function embedding such as BNG and UPF. To make SD-Fabric work with pins and support WCMP, we made the following changes. The ONOS pipeliner is adapted to work with SOI.P4 by using pure L3 routing instead of MPLS for the forwarding on the spines. However, adding the support of MPLS and SRv6 on SOI.P4 is considered for the future. We also added a WCMP handler in SD-Fabric that periodically calculates and adjusts weights of the next hops based on the current topology, We use a trivial algorithm that finds the weights based on the link speed, but the algorithm can be extended to use different metrics such as QS metrics, packet drop rate, etc. In the future, we consider adding side generic extension mechanism to extend the pipeline functionality. Here we provide an example that compares WCMP with ECMP for an unbalanced fabric of 2 by 2. As you can see, links have different speeds. In ECMP, weights are all equal to 1. Now consider L2 is forwarding a 150 gigabit per second traffic to L2, which in this case is equally distributed through the links. As you can see, links from L1 to S2 and S2 to L2 are fully saturated, and if the traffic exceeds 150, packets will be dropped in those links while other links are underutilized. WCMP distributes the traffic through the links proportionally to the speed by adjusting the weights to 811. In this case, 80% of the traffic will be forwarded to S1 and 20% to S2. So links are now equally utilized. Here the traffic can be increased up to 500 gigabit per second before links are fully saturated. Now consider that link failure happens between S1 and L2. If we use the same weights as before, the 200 gig link is utilized as twice as other links, and it will start dropping packets if the traffic exceeds 250 gigabit per second. Note that we prefer to drop the packets at the source, not inside the fabric, as it's waste of the network resources. In this case, the WCMP handler recalculates the weights considering that the maximum supportable rate on the pass-through S1 is not 400 gig anymore, but it's now 200 gig, as the link between S1 and L2 is bottleneck. So the weights are readjusted to 411. Again, having a 150 gigabit per second traffic in L1, now less traffic is sent to S1 and more to S2, so that links are now equally utilized at 50%, except the 400 gig link, of course, and the fabric now can support up to 300 gigabit per second traffic before links get fully saturated. Now I hand it over to Daniele to demonstrate the WCMP functionality on a similar live environment.
Hi, I'm Daniele Moro, and now I'm going to show you the demo. The setup is composed of an unbalanced 2x2 leaf spine fabric. All the switches are running SONiC and the pins software stack, and are controlled by ONOS. The SD Fabric control application running on top of ONOS is in charge of controlling the forwarding of the traffic inside the fabric. Let's now log in into ONOS via the graphical user interface. We are now pushing the network configuration into ONOS. That contains information like the management address that's being used by ONOS to connect to the devices via the P4 runtime protocol. ONOS is also able to detect links by using LLDP packets. ONOS is injecting them into the network via packet outs and trapping them from the devices via packet ins. ONOS is also able to discover hosts by trapping ARPS packets while are being sent by the host. We have a set of applications running on top of ONOS, like the LLDP link provider application, the P4 runtime driver and protocol, but also the pins and SI driver and pipeliner, and the SD Fabric control application that's in charge of controlling the forwarding inside the fabric. ONOS is currently connected to 4 devices, 2 leaf and 2 spines. If we look at the flow entries in Arista2, one of the leaf, we can see that ONOS, and in particular the SD Fabric control application, is pushing down a set of table entries like WCMP table entries, next hop and router interfaces, and routing entries. Looking at one of the WCMP table entries, we can see that right now ONOS is using ECMP, equal cost multipath, to forward the traffic towards the spine. Indeed, the weights in these WCMP table entries are all equal to 1. However, the topology that we're using for this demo is heavily unbalanced. As we can see, the leftmost leaf, Arista 2, is connected to the spines by different links and link speed. We have a 400G link towards Arista 1 and two 50G links towards wedge 100BF. Let's now see how the traffic is being distributed and forwarded inside the fabric. We are going to do that via the SONiC CLI by using the SONiC port counters. Traffic is currently generated from Arista 2 towards Arista BF, so must travel through the spines. On the top, we have the Arista 2 port statistics, while on the bottom, the Arista BF port statistics. As you can see, we are using ECMP, and the traffic on Arista 2 is equally distributed on all the links towards the spine, port Ethernet 0, Ethernet 16, and Ethernet 20. But the link utilization is very different. Let's now see how weighted cost multipath works. ONOS is now configured to use WCMP rather than ECMP. And we can see that going to the Arista 2 flow entries, where the WCMP group table entry, that before was using all weights equal to 1, is now using weights proportional to the link speed. Weights are 1, 1, 8. 1 and 1 are the weights being used for the links between Arista 2 and the wedge 100BF, so the 50G link, while the weight 8 is the weight used for the 400G link between Arista 2 and Arista 1. And weights are reflected on the traffic distribution inside the fabric. As we can see from the top, the Arista 2 ports statistics, we can see that now the amount of traffic sent on the Ethernet 0 port is more or less 8 times the amount of traffic sent on Ethernet 16 and Ethernet 20. But now the link utilization is the same for all the links exiting Arista 2. Let's now introduce a failure into the network. From the Arista BF CLI, we are going to shut down Ethernet 0 and Ethernet 8, so two of the 100G link between Arista 1 and Arista BF. ONOS is able to detect a link failure because it's not receiving LLDP packets from certain port. Links were 8 at the beginning, and now ONOS is detecting link failures, and we have 6 links in total. Meanwhile, ONOS is also rebalancing the traffic inside the fabric by adjusting the weights of the WCMP table entry. The trivial algorithm that we have implemented in the WCMP handler is calculating the minimum capacity of all the paths between the leaf and adjusting weights accordingly. As we can see, the table entry that before had 118 as weight has now 114 as the weight, because the capacity between Arista 1 and Arista BF has reduced to 200G. The new weights are also reflected on the traffic distribution inside the fabric. The below statistics are the one from Arista BF, and we can see that now Ethernet 0 and Ethernet 8 are shut down, and the traffic is being received only on 16, 24, and 32. While on Arista 2, the top statistics, we can see that now traffic on Ethernet 0 is 4 times the traffic on Ethernet 16 and Ethernet 20, proportional to the weights that we set in the WCMP table entry. And this concludes this demo. Summarizing, during this demonstration, we've seen how Pins is bringing SDN capabilities to the SONiC network OS. We've seen also how STFabric and ONOS are used to program routing tables with weighted cost multipath that helps in optimally exploiting network, especially when unbalanced. We also seen how the SDN controller can dynamically adapt weights based on the network condition. Thank you for your attention, and we encourage you to try out pins, add new use cases and capabilities, or build new innovative WCMP algorithms on top of ONOS.